Once again, I'd like to do an example of a physics problem that we don't have time for in class. This time to give you an example of static equilibrium and how to solve for unknown forces and torques when you have a problem that's a static equilibrium problem. The problem I want to look at this time is, in fact, the one that's described in our handy class handout on solving static equilibrium problems. I'll describe it in detail here, though, just so you can hear it. What you'll see on this little handout, I'll show you the picture on here. We have a wheel of mass m and radius r that rests on a sloped surface. The angle of the sloped surface compared to horizontal is theta, and it's not slipping. It rests there without slipping, so there's enough static friction to keep this from slipping down the hill. And the wheel is also being held in place by a horizontal force applied to the top of the wheel pulling backward. I'm picturing this as some sort of a strap or something wrapped around the wheel being pulled exactly horizontally at the top of the wheel. And so in terms of those variables given, my question is, how hard do I need to pull on that strap? How hard do I need to pull on the strap up here in order to keep the wheel from rolling or sliding down the hill? So that's our setup. And the first step in solving any static equilibrium problem like this is going to be to draw an extended free body diagram for the system. And remember, an extended free body diagram is just a free body diagram that shows where all the forces on the system happen to act. So the first force is actually easy. It's already drawn up here. It's the force of the strap. Force of the strap, F. And I just called it F in the diagram. Very generic name, no subscripts or anything. That's our unknown force, and it acts at the top because that's what I told you it did. Other forces, well, as usual for free body diagrams, we look through the whole thing and we say, well, I have a contact point with the outside world here where I'm touching the slope that I'm sitting on. So if I'm touching that point, anytime I have a contact point, I should assume there's going to be a normal force that's perpendicular to the surface of contact. That means there's going to be a normal force pointing like this, pointing up that way. And every time I have a normal force, I also usually ask, do I have a frictional force going with this? Anytime I have two surfaces in contact, I ask myself, do I have to worry about friction? In this case, the keywords no slipping tell me there better be a frictional force there. Which way is it going to be? It's going to be a force of static friction that keeps it from slipping down. So there must be a frictional force of static friction, pointing up the hill at that contact point. Again, I've drawn both of these at the contact point because that's where static friction and normal forces act. That's all the contact points with this. The other force we have to deal with is the long-range force of gravity, of course, weight, the weight of this wheel. And the weight force goes straight down, right here, straight down from the center of the wheel. So that's our that's our extended free body diagram for this problem. It seems to be, it's got all our forces labeled. That's taken care of. And so now that I've drawn that, the final thing I need to do when I'm drawing an extended free body diagram for a static equilibrium problem, I have to choose a pivot point. You'll recall that every possible pivot point is equally correct, but that some are going to make my life much easier than others will. In particular, I want to choose a pivot point at some place that will make as many forces as possible, especially unknown forces, drop out of my torque calculation. So of course, I know as soon as I've drawn any kind of free body diagram, extended or not, I know that in static equilibrium I can use Newton's second law to conclude that the x component of net force has to equal 0, and the y component of net force equals 0. Those I have regardless of the story. And so I could even go through and write down those components if I needed to right now. But I know that's true. The question, and that's based on an ordinary free body diagram, not caring where a pivot point is, not caring where the forces act. Those two I could write down right now immediately. But I know this is going to be a static equilibrium problem. I know I'm going to need to solve for torques as well. And because there's some rotation of I'm trying to stop this wheel from rolling down the hill. So with that in mind, I know I've got to choose a pivot point. So I want a pivot point where many forces won't give a torque. And I can suggest 3 likely places for a pivot point that we might consider. Just different things you can think about. One of them, an obvious choice for a pivot point, would be the center of the wheel. I could choose that to be my pivot point. And what would be the advantage there? Well, I would know, for example, that the weight force it acts at the center of mass of the center of gravity of the wheel, and so that weight force acting at the center means it will give no torque. You recall the torque equation, that torque due to some force is equal to, in our notation, plus or minus the distance from the pivot point times the magnitude of the force times the sine of the angle phi between the direction to the pivot point, or from the pivot point to your force, and the direction of the force itself. We'll say more about that when we get to the calculation point. It's that, but here the R is 0. My weight force acts at this pivot point, so it would not contribute. In fact, it's even better than that. I can look at the other forces here. I know that this force by itself would create a rotation like this around my chosen pivot point. That's going to be my, I'll call this direction, as usual, our plus theta, our positive angular direction. So this force would give me a positive torque. The frictional force, the static friction force, would give me a negative torque around that central pivot point. But the normal force, you'll notice the normal force, its line of action passes right through that pivot point. So here both the normal force and the weight force would give me no torque. And the problem would reduce to a competition between the pulling force up here and the frictional force down here, I'm balancing those out. So that's one choice, would be to put my pivot point at the center. Another choice I could consider would be putting a pivot point down here at the contact point. I could put my pivot point there. For that choice, I would see that my normal force acts at that point, so it gives me 0 torque. I see that my frictional force acts at that point, so it gives me 0 torque. And then what I'm left with is the weight force by itself would rotate in the negative direction. It would cause a negative torque, with this being positive. This pulling force would give me a positive torque by itself. Those cancel out, or our problem then would reduce to canceling out the torques due to the weight force and this pulling force. That's my second option. The third option I might present would be, hey, we could put a pivot point at the very top. Conceptually, it's as if we're hanging the thing from there. The advantage there is that this force, F, the pulling force, would give no torque around that, so it wouldn't contribute to my torque equation. The weight force would be pulling straight down, and you can imagine if that were the only force, it's not going to make it rotate at all around this pivot point. And again, that's because the line of action of the weight force passes straight through that. So my sine of phi in my torque equation will come out to be sine of 0, which is 0 in this case. So that would give no torque. So in this case, if this were my pivot point, the calculation would come down to a competition between the normal force. Normal force by itself would just barely create a positive torque around this pivot point, and my frictional force, which would create a negative torque around this pivot point. So each one of those 3 choices for pivot point would give me 2 of my 4 forces giving 0 torque. From that perspective, they all sound pretty appealing. But let me tell you, the one that I really like is this one, because the normal force and the frictional force are both unknown forces. And not only are they unknown forces, they're not forces that I care about. The only force I want to calculate is this force up here. If I can avoid calculating the normal force and the static friction force, if I can just avoid ever having to work out what they are, what those values are, I'm going to be happy. So I want to choose this contact point as my pivot point. That's my pivot point, and I'll use that as the basis for my torque equation. So as I just said, that means that the torque due to the normal force equals 0, and the torque due to the frictional force equals 0. Both those torques come out to be 0 for this pivot point. What about the others? Well, we know we have to write this as R times F times sine of phi. We have to include information about, well, plus or minus, the direction, the distance from the pivot point, the strength of the force, and the direction, and the angle, phi, between those 2 things. And I could go through and talk and calculate the angles here. It's going to turn out that one of our alternative forms of that torque equation is going to be more convenient for doing this calculation. Specifically, we remember that one of the alternate forms of this is to write this as plus or minus r perpendicular times the magnitude F. R perpendicular, remember, is the moment arm for a given force. So let's spell out what that is in our particular case. For the weight force acts straight downward, so its line of action is this vertical line extended infinitely vertically like that. And my moment arm is going to be, so line of action of the weight force extends down and up like that. And so the moment arm I have is this perpendicular distance, perpendicular to the line of action of the force. It is the distance from the pivot point horizontally, and you can work out that's equal to r times sine of phi for the angle between the two. So I'm just going to leave it this way. This is my r perpendicular for the weight force, this distance. And hey, that's something that we can work out because we know some of the angles in the problem. We know that the angle, we know that the angle theta, excuse me, is this angle up from horizontal of the ground. We know that this is the angle theta. And so there are some wonderful theorems we can use to tell us that as this flattens, let's see, so that's theta. I'm just going to be really explicit here. Let me find an angle. Basically, I'm looking at this, I'm looking at the triangle that I can draw up here, like so. I'm looking at that right triangle that I can draw that has the weight vector over here. I want to find this length. I know that this side, this thing, is the full radius, capital R, of the circle. So that's my radius. And I want to find one of these two angles so I can use some trig to find our perpendicular. So I can calculate out what that'll be. Well, let's see. That's theta. So if theta is the angle from horizontal there, then this must be 90 degrees minus theta. And so that means that this angle here is theta again. And so if I wanted to, this will be 90 degrees minus theta, and this up here is going to be theta. And just as I'm just sort of trying to work out where I can put an angle theta into this triangle, put my angle in here. And I've just been looking at 90-degree angles, comparing 90-degree angles and 90-degree angles and subtracting. Again, we can make sure this works though. If we take theta in the limit where theta goes down to 0, you can immediately see that this angle will also go down to 0. So it does the right thing. It's the right sort of angle to make this work. As this goes down to 0, the angle down here would get bigger. So this is the angle we want. That's our theta. And so in particular, I can say then that the torque due to the weight force is going to be, well, okay, remember, it's going this way. If this was my pivot point, if this is my pivot point over here, then the weight force by itself is going to create a negative torque, with our conventions for what plus theta is, a negative torque, and the r perpendicular is going to be the total radius times the sine, let's see, yeah, sine opposite, so it's sine of phi, that's my r perpendicular, times the mass times gravity. mg is the magnitude of my weight force. So there I have my torque due to the weight force. Then I can do the same thing for torque due to my pulling force up on top. And what will I get there? Torque due to my pulling force? Well, I still need to find an r perpendicular. My line of action for this pulling force is all the way up here. That's my line of action. And so my r perpendicular for the pulling force, r perpendicular for the pulling force, is this whole vertical distance. That looks like a weird thing to keep track of, finding that whole vertical distance there. But we can be sneaky about this. We know that this distance is r, capital R, the full radius of my wheel. And then the other distance I have to get down to this level is part of that same triangle I just figured out. That's kind of cool, actually. I can use, this is now the adjacent side to that angle theta. So I can write down my torque here as being, well, let's check. Here's my pivot point. This force is making the wheel go that way, the positive direction. So it's plus. My vertical height is r plus r sine phi, or sine theta. Sorry, that was supposed to be a theta. That was supposed to be a theta. So this one is going to be r plus r times, and cosine is my adjacent side, r times cosine theta times whatever my magnitude of the force F is that I need to solve this. So there I have my list of all the torques in the system. I've got these 4 torques, or sorry, 1, 2, 3, 4 torques on my system, where this was my chosen pivot point. Again, I could have chosen any other pivot point, and I'd still have a valid equation that would move me toward the solution. The advantage here is that none of my torque equations have these unknown normal force and static friction force in them. All right, now that I've dropped all this stuff, so I've got my torques. Let me go and write down then the net torque equation. That net torque, didn't quite get that. That net torque, tau net, equals 0. And in our case, that net torque is just normal force torque plus frictional force torque plus my weight torque plus my pulling force torque. Just adding them all up. In our case, that means 0 equals, well, 0 plus 0, I'll just leave those out, minus r sine of theta times mg plus, and I'll factor out an r from this. I can write this as r times 1 plus cosine of theta times f, just to factor that out, plus r times 1 plus cosine of theta times f. I've written that all out. That equals 0. And at this point, looks like I'll need one more line. At this point, I just want to solve for my unknown. My unknown, of course, is just that pulling force, F. The radius, it turns out, I just want to get that by itself. The radius will cancel out. If I divide both sides of this equation by capital R, by the radius of the circle, then that goes away. That's handy, that it cancels out. So I'll add this term to both sides, and I'll divide by that 1 plus cosine theta. I'll end up finding the following equation for F. F equals sine of theta divided by 1 plus cosine of theta times the weight, mg. And that is my answer to the problem. You can check the units. Mg is mass times the gravitational acceleration. It's kilogram meters per second squared, so it's in newtons. That'll be that has the correct units for force. Sines and cosines have no units, so this works out nicely. And I've got this thing. I've come to this. Let me do a double check or two to check my answer. If theta were equal to 0, so this whole thing were flat, I would hope that I wouldn't have to pull it all to keep it from rolling or to keep it from sliding. And indeed, if theta equals 0, sine of 0 equals 0. That's handy. I could do a lot of other limits to check things, but I'm pretty happy with how that's come together. I think, doing anything else, I guess, is going to be hard to manage. I haven't said anything about what frictional coefficient I need here, so it would be hard to do other limits. The neat thing about this example is we've gotten to an answer. Because we cleverly chose our pivot point, we've gotten to an answer for the force that we need without ever having to calculate the normal force or the frictional force magnitudes. We were able to get rid of them by choosing, or to ignore them rather, by choosing a clever pivot point. If I had chosen the center as my pivot point, some of my distances and angles would have been easier to calculate. I wouldn't have needed this complicated or perpendicular stuff, but I would have needed to calculate the frictional force. And to do that, I would have needed to do all of these equations, not just the torque equation, but also the x and y components of Newton's second law, the net force equals 0. So this is a nice little solution. It comes through and shows you how, by choosing pivot point wisely, we get to calculate an unknown force in a problem like this. If you needed to know the normal force or the frictional force, the next step would be to use Newton's second law and calculate them using the net force x and net force y equals 0. I think that's it for this.